Howdy, this is a video on section 7.1 from the textbook by Suppess and Hill. We're dealing with the commutative axiom. It's part of chapter 7 where we're going to build a simple mathematical system. Before we proceed, I believe it's important to review two rules found in the Suppess and Hill textbook. The first is from section 6.3, and that's the rule of identity. The second is from section 6.4, and that's the rule of logical truth. Both are essential in what's to come. In regards to the rule of identity, it's really a substitution. For example, if x is identical to y, then when x appears, we can substitute y in for x. Likewise, if x is identical to y, then when y appears, we can substitute x in for y. Consider this example. Say we're given the premise that x is equal to y. That is, x is identical to y. The second premise, we're given y. And the third premise, we're given if x, then z. So these are our premises, and we want to prove that z is in fact the case. The only way we can do that is through identity. Because x is identical to y, we can substitute that y in for that x. Thus, for line 4, we can say if y, then z, by the rule of identity, with lines 1 and 3. So line 1 allowed us to make that substitution. And then for line 5, we can do our modus ponens inference to get z because of lines 2 and 4. Here's another example. Let's say we're given that 2 is equal to 1 plus 1, and we're given that 3 is equal to 2 plus 1. These are our premises, and we want to prove that 3 is equal to the quantity 1 plus 1 plus 1. Once again, we need the rule of identity, and we can do it in just one step. We can say 3, therefore 3 is equal to the quantity 1 plus 1 plus 1 because of the rule of identity with lines 1 and 2. We're told that 2 is identical to 1 plus 1. And so for this 2, we can substitute in that 1 plus 1. Finally, for the rule of logical truth, a tautology, which includes a simple statement of something being identical to itself, can be inserted into any line of a proof. You can take a tautology and add it wherever you want. No problem. For example, let's say we're given the premise that if x, then y, and we're given the premise if not x, then z. So these are our premises, and we want to prove that y or z is the case. We want to prove that disjunction. And here we can resort to the rule of logical truth. For line 3, we can say x or not x. That's a logical truth because it's a tautology. And then we have proved we can't infer that y or z because we have a constructive dilemma with lines 1, 2, and 3. Because if x is the case, then you get y. If x is not the case, then you get z. Here's one more example. Let's say we're given the premise that 3 is equal to 1 plus 2, and we're also given the premise that 2 is equal to 1 plus 1. These are our premises, and we want to prove that 1 plus the quantity 1 plus 1 is equal to 1 plus 2. How can we do that? We're going to have to use the rule of logical truth. Consider this equality. Think about the left-hand side. This 1 plus the quantity 1 plus 1 appears nowhere else. It appears in no premise. However, with the rule of logical truth, we can say that 1 plus the quantity 1 plus 1 is equal to 1 plus the quantity 1 plus 1, because that is a logical truth. Something is identical to itself. And now we can resort to the rule of identity, because we're told that 1 plus 1 is identical with 2. So we can substitute a 2 there. For 4, therefore it follows that 1 plus the quantity 1 plus 1 is equal to 1 plus 2 by our identity rule with 2 and 3. Okay, we will start section 7.1. Now in chapter 7 of the textbook, we wish to construct a simple mathematical system. Based on only a few fundamental premises, we will be able to derive a multitude of conclusions. We'll start with the commutative axiom. And this is a fundamental premise. Moreover, as an axiom, it is also universal in scope. And because it is universal in scope, we need the universal quantifier. If we express the commutative axiom in first-order predicate logic, we have two quantified variables, x and y, and we'll say that for all x, for all y, x plus y is equal to y plus x. As you know, for example, in arithmetic, 2 plus 3 is equal to 3 plus 2. The order is not important. In addition to axioms, such as the commutative axiom, we will add additional premises called definitions. We have the definition of 2, 3, 4, and 5. Presently, we have a total of 5 premises because we have 1 axiom and 4 definitions. We can derive or prove theorems from them. So we'll use this as our starting system and then derive various theorems. Deriving some theorems. We have this toolbox, and within this toolbox we have the commutative axiom and some definitions. 4 definitions to be exact. And these are taken as premises. We will then attempt to derive some theorems. However, note that when we do prove a theorem, it then becomes a part of our toolbox. We can then use that theorem as a premise in further proofs. For instance, if we prove theorem 1, we are thereby justified to place it in our toolbox. We can use theorem 1 as a premise in other proofs. And that's very helpful because we don't have to constantly reprove theorem 1. And now let's try to prove theorem 1. We have 3 is equal to 1 plus 2. If we look at our toolbox, we do have the definition of 3, but here we are told that 3 is equal to 2 plus 1. That's not exactly the same as saying that 3 is equal to 1 plus 2. However, we do have the commutative axiom. And that gives a hint that we should say that this statement here and this statement here are identical. But to do that, we need the commutative axiom. Without the commutative axiom, we couldn't do it. So for line 1, we'll say that 2 plus 1 is equal to 1 plus 2, and this is just the universal instantiation of the commutative axiom, with x being 2 and y being 1. Note that in some other textbooks you can only instantiate one variable at a time, but in the Suppess Hill textbook you can instantiate multiple variables at the same time in the same line. Alright, so now we have 2 plus 1 is equal to 1 plus 2. We just instantiated the commutative axiom. For line 2, we can then say, because we know that 2 plus 1 is identical to 3 by the definition of 3, we could just substitute 3 in for that 2 plus 1. Hence we say 3 is equal to 1 plus 2 by the identity of definition 3 with premise, or not premise, but with line 1. For theorem 2, we have 4 is equal to 1 plus 1 plus 2. Let's do a little scratch work before we jump into the proof. We can rewrite this expression. We have an equality, and the right-hand side is 1 plus 1 plus 2, but this is just 4 is equal to 1 plus 3. We can rewrite that. And this gives us a clue that we should use, for example, the definition of 4, which tells us that 4 is equal to 3 plus 1. But here we have 1 plus 3. We want 3 plus 1. And so we're going to have to do the commutative axiom. We're going to instantiate it. So let's do that. For line 1, we could instantiate that 3 plus 1 is equal to 1 plus 3. This is the universal instantiation of our commutative axiom, with x being 3 and y being 1. For line 2, we can say that 4 is equal to 1 plus 3. Because here we have this 3 plus 1, we know by the definition of 4 that that's identical with 4. So I just substitute 4 in there, and this is just the identity rule with the definition of 4 and with line 1. And now, notice that we do have theorem 1 in our toolbox, that 3 is equal to 1 plus 2. And so we can substitute that 1 plus 2 in for that 3. Thus, for line 3, we can say, therefore, it follows that 4 is equal to 1 plus 2 by the identity with theorem 1 and with line 2. We didn't have to prove theorem 1. We've already done so. It's in our toolbox, so we can use it. Otherwise, obviously, the proof for theorem 2 would have been longer. So now let's place theorem 2 in our toolbox. For theorem 3, we have 1 plus 1 plus 1 plus 2 is equal to 2 plus 3. Okay, so what should we do? The best thing here is to deal with this left-hand side. We could just say that 1 plus 1 plus 1 plus 2 is equal to itself. We could just use the logical truth rule. Thus, for line 1, we'll just say that 1 plus 1 plus 1 plus 2 is equal to 1 plus 1 plus 1 plus 2, and that's just a logical truth. Because now, all we have to deal with is the right-hand side. We have to deal with this quantity. We want that to be 2. And we can deal with this quantity. We want that to be 3. If we look at our toolbox, we have the definition of 2. And that's just 1 plus 1. So we'll use the identity rule. So for line 2, we'll say that 1 plus 1 plus 1 plus 2 is equal to 2 plus 1 plus 2 by the identity with definition 2 and with line 1. And now we just have to deal with this 1 plus 2. We want that to be a 3, but according to theorem 1, 3 is equal to 1 plus 2. So let's resort to that. For line 3, it therefore follows that 1 plus 1 plus 1 plus 2 is equal to 2 plus 3 by the identity rule with theorem 1 and line 2. Exercise 1b tells us that these axioms, definitions, and theorems for addition can also be used in proving conclusions derived from particular given premises. For example, in number 5, we're told to prove that 5 is greater than 2, and we're given 3 premises. But we also have our toolbox with the commutative axiom with some definitions and some theorems. The first thing I like to do is just to relate the various numbers we have. But let's first just state the premises we get with problem number 5, we're told that for all x, for all y, if y is greater than 0, then x plus y is greater than x. Premise 2 is simply 3 is greater than 0, and premise 3 is 3 plus 2 is equal to 4 plus 1. The first thing to note is that we do want to prove 5 is greater than 2, and obviously 5 is the same thing as 3 plus 2. 3 plus 2 shows up here, so we're probably going to use that. Then the question is, what are we going to do with premise 1? How are we going to instantiate that? Well, we have this y is greater than 0. Here we have this 3 is greater than 0, so it looks like we're going to instantiate 3 for y. And then what about x? Probably 2, because that shows up as a number we want. So for line 4, we can get, if 3 is greater than 0, then 2 plus 3 is greater than 2 by the universal instantiation of line 1, with x being 2 and y being 3. Moreover, according to line 2, 3 is in fact greater than 0. Thus we can do a modus ponens inference. Thus for line 5 we can get 2 plus 3 is greater than 2 by modus ponens with lines 2 and 4. We're going to want to relate this 2 plus 3 with this 3 plus 2. Line 3 tells us that 3 plus 2 is equal to 4 plus 1. These things are not in the same order, thus we're going to have to resort to the commutative axiom. Thus the first thing we should do is just say that 3 plus 2 is identical with 2 plus 3. So for line 6, I'll put this over here. For line 6, we'll say that 3 plus 2 is equal to 2 plus 3 by the universal instantiation of our commutative axiom, with x being 3, y being 2. And so we can relate this 2 plus 3 on line 5 with this 3 plus 2. And then this will allow us to relate it to line 3. Okay, so for line 7, we can say that 3 plus 2 is greater than 2 by the identity rule with lines 6 and 5. Moreover, according to line 3, again we have 3 plus 2 is equal to 4 plus 1. But this 4 plus 1 shows up here in the definition of 5. So let's just say that 4 plus 1 is 5. So for line 8, we can say that 3 plus 2 is equal to 5 by the identity rule with the definition of 5 and with line 3. So now we have this 3 plus 2 is identical with 5, so we can substitute that 5 in. Thus for line 9, it does follow that 5 is greater than 2 by the identity of 8 and 7. Here are exercises C, D, and E on page 244 of the Suppess textbook. C states that addition is a binary operation of numbers that is commutative. Give an example of a binary numerical operation that's not commutative. Well, something like subtraction, for example, right? So A minus B does not equal B minus A. Give an example other than addition of a binary numerical operation that is commutative. Well, multiplication. So A times B is equal to B times A. Give a second example of a binary operation that is not commutative. Well, division. A divided by B does not equal B divided by A. We'll continue building up a mathematical system using logic. Up next is section 7.2, the associative axiom. Thank you for watching.